In my last video, I introduced the concept known as a relation, and I showed, the basic properties of them. But in this video, we're going to be talking about some more properties of relations, and we're just going to be doing more stuff about relations in this video. This is like part two to the last video. In the last video, we thought about relations just as, any set of ordered pairs. But it's often more useful to think of relations as, actually describing a relation. And we can do this using, a small change of notation. And the motivation for this new notation is the fact that we often describe, relationships between two objects by displaying the two objects, or the names for them, I guess, and then adding a little symbol between them to describe what that relation is. So, for example, here, the symbol would be less than because x is less than y. That's the relation. So in a similar way, we'll write xr xry to mean the same thing as x comma y is an r, if, assuming r is a relation, of course. Also, you can pronounce this like xry, x is related to y, but in this video I'm just gonna be pronouncing it as x is r related to y, since that's the clearest way to pronounce this. So for example, if we define the less than relation as the set of all a, b, and r2 such that a is less than b, we'll notice that 2 comma 3 is in this relation, but another way of writing this would be 2 is less than 3. So in the last video we defined relation composition as this. We can now define it using the notation we just introduced to define it as a set of all AC and A cross C, such that there's a B and B where A is R related to B and B is S related to C. Another way to think about relations is using pictures. So for example, if you let X be your relation from A to B, then in this picture you can use really any shape to represent the sets themselves, and dots to represent the elements in those sets, and arrows to represent which element is R related to the other element. So for example, there's an arrow from A2 to B3 in this picture because A2 is R related to B3. And same thing with every other element. And in general, you can do this with any relation. I think so long as the domain and range of the relation is non-empty, I think. But anyway, in such a picture, the dots that represent the elements of the sets are called vertices, which is plural for vertex, not vertexes. And the arrows representing the relations between the vertices are called edges. So there's an edge from A1 to B1 because A1 is R related to B1. So you could use pictures like this to understand the concepts that we went through in the last video better. So for example, the domain of R here would be the set of all elements that have an edge facing away from them. And similarly, the range is the set of all elements that have an edge pointed towards them. And also, you could think of R inverse as literally just the same thing, but just all the edges reversed in direction. Pictures representing compositions of relations are a little bit harder to understand. For example, consider this picture, which represents the relations R and S defined up here. We can see in this picture that, for example, A1 is R related to B2, and B2 is S related to C1. So that would mean A1 and C1 are related to each other from the composition of S and R. Or in other words, A1 is S after R related to C1, written like this. And also, notice that there are no elements of the domain of R that are R related to B1, but B1 is S related to C2, but that doesn't matter because there are no elements in A that are R related to B1. So this means that A1 is not related to C2 based on the composition of S and R. And in general, using any picture like this to represent relations, you can only say that, for example, A3 is related to C3 if and only if there is an arrow from A3 to something in B, and then that thing in B has an arrow to C3. Or in other words, you can start from A3 and get to C3 in exactly 2 steps following the edges. Now suppose R is a relation from a set A to the exact same set A. Any such relation like this is said to be a relation on that set. So for example, if we had this relation F to be the set of all ordered pairs in R2 such that the second coordinate is the first coordinate squared, then F would be a relation on R. But how do we draw pictures to describe relations on a single set? Well, one way to do it would be to draw 2 shapes representing the same set, and then, draw the edges between the corresponding vertices. But who really wants to do that? Instead, we can draw it like this, where we don't have to draw 2 shapes representing the same thing. We don't have to even draw shapes, we can just draw the vertices themselves and the edges between them. Pictures like this, used to visualize relations on a set, are called directed graphs. So for example, this directed graph, all of A1, A2, A3, A4 are elements of A, and all of them are related to each other in some way based on R. Same thing as before. For example, A1 is R related to A2 because there's an arrow. There's an edge between A1 to A2. But here, you'll notice that each vertex here has an edge pointing from itself towards itself. Because A2 is R related to A2. When this happens, these edges that relate one vertex to itself are called loops. So in this graph, each vertex has a loop. And because of this, we refer to R as having the property that it is reflexive. And that leads us to our first definition, which says that 1, R is reflexive on A if for all x in A, x is R related to x. So over here, we could see that R is reflexive because there exists a loop for each vertex in this graph. Second definition says that R is symmetric if for all x and y in A, then if x is R related to y, then y is R related to x. We can see that over here, R actually isn't symmetric, because for a graph to represent a symmetric relation, every vertex would have 2 edges facing in both directions instead of just one. But since there's only one direction of these edges in each vertex, then it's not symmetric. And lastly, we say that R is transitive if for all x, y, and z in A, if x is R related to y and y is R related to z, then x is R related to z. And over here we can actually see that R is reflexive and transitive. Since, for example, since A1 is R related to A2 and A2 is R related to A4, and A1 is also R related to A4, and A1 is actually the only element of A you can actually do this on, since you need 3 vertices to do this with. So let's go back to this relation we defined earlier, which is the less than relation. Is this relation reflexive? Obviously not. If you let A be any real number, then there does not exist an A where A is less than A. So the less than relation is not reflexive, but it would be reflexive if you just put a line under to represent or equal to. Then in this case, yes, the less than or equal to relation is reflexive, because A is always less than or equal to A. Now, is the less than relation transitive? Yes, because if you let A, B, and C be real, and if you let A be less than B and B be less than C, then it immediately follows that A is less than C. For a visual representation, you could just let this line represent subset of the number line, and you'll see that A is less than B, B is less than C, and obviously A is less than C. Now, is this symmetric? Hell no. If you let A and B be real, it is never the case that A is less than B and B is less than A. So this, the less than relation, is only transitive. Maybe you've already guessed at this point in the video that the properties of relations defined in the definition I just gave earlier about reflexive, symmetric, and transitive are related to the operations of relations defined in the previous video, which are relation inverse and relation composition. So for example, to say that a relation R is symmetric involves switching around two variables in an order, which is related to R inverse, because that's what you do in R inverse. And the definition of transitivity involves stringing together two ordered pairs that have a common second coordinate and first coordinate, which is obviously related to the composition of relations defined last video. And to understand the next theorem I'm going to introduce, we'll need to define an identity relation. So if we let A be any non-empty set, then the identity relation on A, denoted I subscript A, is the set of all AB in A2 such that A equals B. So for example, if we let A be the set 1, 2, 3, then IA, the identity relation on A, would just be the ordered pairs 1, 1, 2, 2, and 3, 3, since those are the only ones where the second is equal to the first coordinate. If you let A be any set and R be any relation on that set, then this theorem states that first, R is reflexive if and only if the identity relation on A is a subset of R. Second, it says that R is symmetric if and only if R is equal to its inverse. And third, it says that R is transitive if and only if R after R is a subset of R. To prove the first statement, we have to assume that IA is a subset of R. This is true if and only if, for all x in IA, x is in R. This is the definition of a subset. And this is true if and only if, for all x1 in A, x1 is R related to x2. This is true because x is in IA is true if and only if x1 is in A, and x is in R if and only if x1 is R related to x2. Since x1 and x2 are equal to each other, because x is in IA, then we can just replace all the bound variables here to say that for all x in A, x is R related to x. And this is true if and only if R is reflexive. Therefore, R is reflexive if and only if IA is a subset of R. Now we're going to prove the second statement, which says that R is symmetric if and only if R is equal to its inverse. So first we assume that R is symmetric, and we notice that that is true if and only if, for all x and y in A, if x is R related to y, then y is R related to x. Again, which is the definition of symmetric. And since these are bound variables, and these are universal statements, this statement works if you reverse x and y too in the ordered pair. So it also works for yx and xy. So what we get is that this is true if and only if, for all x and y in A, x is R related to y if and only if y is R related to x. And since y is R related to x if and only if x is R inverse related to y, then we get that this is true if and only if, for all x and y in A, x is R related to y if and only if x is R inverse related to y. And this right here is the definition of two sets being equal, or in this case, R and R inverse being equal. So, through a chain of if and only ifs, we've shown that R is equal to R inverse if and only if R is symmetric. And finally, now we're going to prove the third statement, which said that R is transitive if and only if R after R is a subset of R. So first, obviously, we assume that R is transitive. Then we just do the same thing we did with the other two proofs to say that this is true if and only if definition of this. And we can see that over here, this is the precise definition of x being R after R related to z through the composition. Since R's composition with R contains all the ordered pairs that satisfy this. So here we have this is true if and only if for x, y, z, and A. Actually, we don't even need the y anymore, because there's nothing you do with the y in the freaking statement. But anyway, x is r after r related to z, then x is r related to z. Then obviously it immediately follows that r after r is a subset of r, since x, y, and z were all arbitrary elements of A. I'm sorry, this doesn't just follow, it's if and only if, my bad. Anyway, that's it for this video. I think this video is going to be a little bit shorter than the last one. The last two that I posted, but, you know, whatever. Alright, bye.